In this tutorial, we'll progress from our conceptual knowledge about how a CRT works in the previous video, and we'll learn more about the physics formulas that allow us to do a more complete design analysis. In the first section of the CRT, between the cathode and the anode, we accelerate the electrons. We get them up to speed, creating a stream of electrons or a ray. The accelerating force on each electron, that is, F net to the right, is due to them being in an electric field in here. Now, the force varies a bit as the electrons travel between the cathode and the anode. So that makes it difficult to analyze with our force knowledge, that is, F net equals ma. So we use our conservation of energy concept to analyze the change in velocity. E before equals E after. So each electron starts with a potential energy of QV, where Q is the charge on the electron, the elemental charge, and V is the voltage difference between the cathode and the anode, or we can call that the accelerating voltage, VA. Basically, the electrons really want to get away from the cathode, like charges, and towards the anode, unlike charges. And this is the potential energy. And as the electrons move through the accelerating region, they convert the potential energy into kinetic energy, speeding up as they go, until they pass through the anode and out of the accelerating region. So our E after is all kinetic energy, or 1/2 mv squared. And we can rearrange this equation to solve for the velocity given the voltage difference, or we can solve for the required voltage for a given velocity. Next, our electrons enter the deflecting region, much like projectiles. In the deflecting region, we have a different electrical field. This one is perpendicular to the path of the electron stream, which means that the F net on each electron is either up or down, depending on the plate voltage. In our example case here, the F net is pushing down. Thus, our free body diagram looks like this. And note that we don't include the force of gravity, Fg, as it definitely exists, but it's so tiny given the weight of the electron as compared with the magnitude of these electrical forces. So we can ignore this Fg. You can certainly include it if you wish, but it won't make any noticeable impact to your answer. So we'll keep it simple when we can. F net equals ma. With the electrons staying in the middle of these plates, the force doesn't vary much, so we're good to use force analysis instead of energy for this deflection region. The deflection force is due to the electrical force, or EQ, where E is the electric field and Q is the charge on the electron, or the elemental charge. And we have ma on the right, where the acceleration causes the deflection down. Then we can replace the E, or electric field, with V over D, or voltage across these deflecting plates, which we call Vd, and D is the distance between those plates. So we can rearrange this equation to solve for the deflecting acceleration given a voltage difference, or we can solve for the required voltage for a given deflection acceleration. An additional relationship to take from our analysis would be that the deflection of the ray is directly proportional to the deflecting voltage, Vd. That is, the greater the deflecting voltage, the greater the deflection. Also, the deflection is inversely proportional to the accelerating voltage, Va. That is, the faster the electrons are traveling through those deflecting plates, the less time they have to be deflected. So the greater the accelerating voltage, the smaller the deflection. We can, as a result, combine these realizations into this relationship. The deflection is proportional to the deflecting voltage over the accelerating voltage. As the deflecting voltage increases, so does the deflection. As the accelerating voltage increases, we're dividing by a bigger number, and the result is the deflection decreases. So this relationship enables us to make deflection predictions based on previous observations and adjustments to the voltages.